Yes, so here we have the question: heat energy of 735 joules is given to a diatomic gas. Okay, and the gas is allowed to expand at constant pressure. Each gas molecule rotates, okay, around an internal axis, but do not oscillate. Okay, and the increase, so you have to find the increase in the internal energy of the gas, right? So what is the meaning of that? They are rotating but not oscillating, right? So for gases, for monatomic and diatomic, both of them, oscillation happens at very high temperatures. Okay, when the temperature is very high, then the gases, apart from the translation motion and the rotational motion, they also oscillate. So we use that extra energy that has to be demonstrated for oscillation if the temperatures are very high. If it is not oscillating in this case, that means the temperatures are moderate only, right? So we know that the energy for monatomic, it is only translational. Okay, so that's why we say in one direction, translation, half kT is the energy, right? So the energy for a diatomic gas will be given by this. Okay, right. So see, these three parts are for translation motion. Okay, the translation of the molecules. Okay, so for monatomic gas, only these three are present, right? The rotational ones are not considered for monatomic, but since here we have the diatomic gas, we have the rotational contribution, the contribution due to the rotational kinetic energy as well, right? So the CV, okay, the change in internal energy for any gas is, for n molecule, it is given by n CV delta T, right? And for diatomic gas that is not oscillating or vibrating, it is 5 R upon 2 is the CV, okay? The CV, the specific heat capacity at constant volume, right? CV is 5 R upon 2 for a diatomic gas, right? So this was a little introduction, and the heat Q is given by NCP delta T. So I'll explain how and why we are using this formula delta U and delta Q. But this was just an introduction of how the things are. There are 5 parts to the energy of a diatomic gas. Okay, 3 for translation, 2 for rotation. Okay, diatomic gas CV is 5R upon 2. This is the introduction of the thing. Okay, now let's come to the question. What the question is really asking. So for constant pressure, Q is NCP delta T. Okay, if Q amount of heat is given, delta T is the rise in temperature. Cp is the specific heat capacity of the gas at constant pressure. Cp for diatomic gas is given by, that is Cv by R. Cv here is 5R upon 2. 5R upon 2. So Cp becomes, you just add 1 R to it, it becomes 7R upon 2. This is Cp, okay? And the delta U, the change in internal energy of a gas, is given by NCV delta T, okay? NCV delta T, right? So for the gas, if I just take the ratio, Q upon delta U is this thing upon this thing, right? NCP delta T upon NCV delta T. Fine. This cancels, so this is Cp upon Cv. So Cp upon Cv is going to give you 7 upon 5, right? The heat given was 735 joules, and you have to find the delta U, the change in the internal energy of the gas. So delta U can be said to be 5 upon 7 times the heat given Q. That will fetch you 5 upon 7 times 735. If I simplify this, this is going to be 105. 105 times 5 is 525 joule. Okay, that is option number 1 here. So the change in internal energy delta U is coming out to be 525 joules. Option number 1 is the correct answer. Okay, the basic thing that we have to understand is the use of these formulae, Q and delta U formula. This delta U formula is applicable for all gases. Okay, no matter what the process is. Okay, for any process this is true. Delta U is NCV delta T. Q is equal to NCP delta T. So this formula had to be used. Okay, fine. Thank you.